Hello everyone, welcome in this video tutorial on treatment of acidic hydrogens, hydrogen bonds and tautomerism in crystal structure refinement. Hope this video tutorial finds you all in a good health in these COVID times. The crystallographic programs used are OLEX2 and SHELXL, and these programs are available free of charge for the academic users, and the necessary file required for the refinement are used with permission from Dr. Peter Muller and from Mr. Song Adlan. The more detail about the example is available in this book reference, Crystal Structure Refinement, a Crystallographer's Guide to SHELXL, edited by Professor Peter Muller. So before going to the refinement parts, let's have a quick look about the hydrogen atoms. Hydrogen atoms, as we know, are very important in chemistry and they are difficult to localize in an X-ray diffraction because the diffraction power is depend upon the number of electrons in the particular atom. And as we know, the hydrogen atom has only one electron, so its diffraction power is weak and it is difficult to localize, especially in the presence of the heavy atoms using the X-ray structure. With neutron diffraction methods, hydrogen atoms can be found very easily. As we know, the X-rays are diffracted by the electrons, but neutrons are diffracted by the nucleus. Due to thermal motion, the location of hydrogen atom is difficult to determine with the greater accuracy. However, we can assume that the motion of a hydrogen atom is proportional to the motion of the heavier atom to which it binds, and this model is known as a riding model. When including hydrogen atom into our atomic model, we generally do not refine their thermal motion, but assume that the isotropic thermal value or U value of a hydrogen atom is 1.2 times the anisotropic thermal value of the atom to which the hydrogen binds. For methyl group, this factor is assumed to be 1.5 instead of 1.2. In SHELXL, this is achieved by replacing the isotropic U value of the hydrogen atom in the instruction file by minus 1.2. This minus ties the U value of the U value to the UEQ, mean the anisotropic value of the non-hydrogen atom immediately preceding the hydrogen atom in the .ins file. Therefore, it is crucial to correctly position the hydrogen atom in the file so that they directly follow the non-hydrogen atom to which they bind. Then come to the acidic hydrogen atoms, the hydrogen atoms which bind with the oxygen and the nitrogen. Although the standard bond length for the nitrogen-hydrogen and oxygen-hydrogen bonds are well known, it is frequently not clear whether a nitrogen atom or oxygen atom is protonated or not. In such cases, the presence or absence of a hydrogen atom could change the determined oxidation state of a metal atom, and also important in order to achieve electron neutrality, which can be a crucial piece of information for any chemist or a crystallographer. It is considered good practice to include potentially acidic hydrogen atoms into the model only when they can actually be found in the difference electron density map. That means the crystallographer has to find significant residual electron density maxima on positions where a hydrogen atom could be located. If there is no such electron density, the hydrogen atom in question should not be included in the model. This doesn't mean, however, that it is not present. It may be present. It only means it cannot be found based on the diffraction data. Then come to the semi-free refinement of the acidic hydrogen. When good low temperature data is available, the hydrogen atoms can frequently be found in the difference Fourier synthesis and their coordinates can simply be taken from the list of residual density maxima. The so found hydrogen atoms can either be refined using a fixed constraint, mean as a riding model, or in a semi-free way by only restraining the XH distances using the D-fix. This restraint required the crystallographer to specify a target value for the distance. The target value can be found in the .lst file where with appropriate excess bond distances at the temperature specified in the .ins file. So it is very important to specify the temperature of data collection in the .ins file during the crystal structure refinement. As we know, the bond length are fluctuate with the temperature. The target values of D-fix can be taken from there, from the .lst file. Approach for the semi-free treatment of acidic hydrogen atom is elegant and allows for a somewhat less restricted refinement of the hydrogen position. In very rare cases, when extremely accurate high resolution data is available and a hydrogen atom is involved in a strong hydrogen bond, which significantly lengthens the donor hydrogen distance, it may even be possible to refrain from using a distance restraint altogether. In any case, the isotropic U values of a semi-freely refined hydrogen atom should still be constrained to 1.2 times the anisotropic thermal value of the nitrogen or oxygen atom the hydrogen binds to. Sometimes with very good data, one can possibly let the thermal value of the one of the other hydrogen atom refine freely, which I will discuss some in other example. So let's come to the refinement part. This is natural compound eromycin crystallizes in the tetragonal space group I4 bar with one molecule of eromycin and one ethanol molecule in the asymmetric unit. At this point, we are going to join the refinement, where all known hydrogen atoms are refined anisotropically and all hydrogen atoms bound to carbon have been placed, and the hydrogen on the nitrogen and oxygen are still not placed. The crystal diffracted relatively weakly and the data had to be truncated at 0.9 angstrom. As a result, the data to parameter ratio is not very good, which is the reason why we are using the ADP restraint SIMU and DILU for all the non-hydrogen atoms. Also, there is one ethanol molecule near to the special position which is refined using the part -1 instruction. This is ethanol which is close to a special position and it is refined using the part -1 instruction and it is only half occupied. So now our next job is to place the acidic hydrogen on the nitrogen and oxygen. So for this, if I am going to see the map, electron density map, just by pressing the Ctrl M on the keyboard, I can see there is electron density on this oxygen atom, which is due to the hydrogen atom, or it is OH group, and there is also electron density on this nitrogen atom. So I am going to put off the map by pressing Ctrl M, and now just refine first. Okay, so now if I want to locate the hydrogen on this oxygen and nitrogen, it seems to be a hydrogen atom here and this seems to be hydrogen atom here. So first let's place the hydrogen on this oxygen atom, and this Q peak is very appropriate for the hydrogen atom, and let's select this one and name H This is I think oxygen 3, so name H3O. Okay, and select this bond and type D fix 0.84, which is a standard oxygen hydrogen bond length. And now if I am going to select these two atoms, and the D fix is here, and this H3O hydrogen atom is placed below the oxygen atom, and now change this as minus 1.2. Okay, now let's refine first. Now the R factor is dropped to 6.63, and there is hydrogen on this oxygen atom. Now if you look at the position of hydrogen on these nitrogen and oxygen atom, there is hydrogen seems to be on this nitrogen, and there is one more hydrogen seems to be present on this oxygen atom O1. But due to tautomerism, it is not clear which oxygen is protonated and which is not protonated. For this, let's have a comparison of the three possible tautomers. So these are the possible tautomers. In the first tautomer, this nitrogen is protonated and this oxygen is also protonated. In the second isomer, this nitrogen is protonated, this oxygen is not protonated, and this oxygen is protonated. In the third isomer, this oxygen is protonated and this oxygen is protonated, and this nitrogen is not protonated. So how can we know which one is protonated? So only 2 out of 3 heteroatoms, mean 2 oxygen and 1 nitrogen. So out of O2, O1 and N1, only 2 are protonated for the electroneutrality. So which one is protonated? If you look at the third tautomer, you can see there is carbon nitrogen double bond and there is carbon nitrogen single bond. So these two bond lengths are different. But in tautomer 2 and tautomer 1, the bond length are single bond. So these two bonds should be same. If you look at this bond, this is 1.367 and this is 1.369. So these almost are very same. So these should be single bond. So possibility of this tautomer is ruled out. So now we have to decide between these two tautomers. So in tautomer number 2, there is carbon oxygen double bond. So if you look at the bond length, this is very close to the carbon oxygen double bond, 1.265 angstrom, and this distance is 1.334. So this is clearly a single bond. So this is double bond. So this is not protonated. This nitrogen is protonated and this oxygen is protonated, which is also spotted by the electron density peaks appearing near the nitrogen number N1 and oxygen O1. So oxygen O1 is protonated and N1 is protonated and oxygen O2 is not protonated. So tautomer 2 is predominant in this case. Okay, so now let's place the hydrogen. Now select this cubic and type name H1N and enter, and select this bond and type D fix 0.88. Now you can see the D fixed state is placed on the N1 H1N, and this hydrogen atom is lie below this nitrogen atom. If you note here, just copy and paste below the respective atom and type it as minus 1.2. Okay, now let's go to refine. So the R factor is further dropped to 6.46%. That's good. Let's refine one more time. And now we can see this oxygen is protonated, should be protonated. but cubic density is not appearing near this one. Let's increase some cubic density to up to 20, and let's refine. Now you can see the cubic is appearing this around this oxygen atom, and this distance is 1.334. So this should be a carbon oxygen single bond. Now select this oxygen, so this cubic, and type name H1O. This is O1, so H1O. Just enter. Select this bond and type dfix 0.84. Now you can see the two atoms in the .ins file, and don't forget to write here minus 1.2, and okay. Now refine. Yes, the R factor is further dropped to 6.34%. Now comes to this oxygen atom. As we know, this oxygen atom or this ethanol molecule is near a special position, so it is only half occupied. So we need a hydrogen atom which is only half occupied. So this is O1s. Select this cubic and type name H1s, and select this bond and type dfix 0.84, and now select these two atoms, and this atom lies near this one. So just copy and paste it here below this one, and now this atom is oxygen atom only half occupied. Change occupancy to 10.5 and type minus 1.2, and okay, refine. Okay, now R factor is further dropped to 6.31%. Now you have placed all the hydrogen atom on the acidic atom, and the refinement should be converged. Yes, it's converging slowly and it is settled down. So oxygen is 3.5 because this oxygen is only half occupied. Okay, so we have discussed about the acidic hydrogen and the tautomerism, and now come to the hydrogen bond. So first put off the cubics by pressing Ctrl Q, and now type H tab, and you can see the hydrogen bond with donor receptor distance of 2.9 angstrom and minimum angle 120. It will search, and it found 3 hydrogen bonds here: O1, O3, O3, O2, and N1, O2. Okay, so now next step is to type H tab minus G to show the hydrogen bond, and press enter. Now these are the hydrogen bond. You can see this is select this oxygen, select this hydrogen, and if I am going to label, there is option label, type label, and now select this distance and type label. Now can you move this label by using the shift key? So this bond length, this H1O3 hydrogen bond length is 1.88 and 5 is the ESD. So if you are going to type text, you can find the hydrogen atom at the end of the text here. These are the hydrogen bonds. There is no ESD still. You can even calculate the ESD. What you have to do, select this bond and type ESD, and you can see the bond distance is 1.885 angstrom. Similarly, these bond distance can be calculated by typing ESD, this distance is, here you can find the angle, sorry. Now select this one, type EST, and this distance is 2.035 angstrom. So these distance can be listed in the respective file, or if you want to include more hydrogen bond, just type fuse, and this time you can put off this level, right? Okay, so if you include some more hydrogen bond, then type H tab. Suppose you want to include the hydrogen bond longer than 2.9 angstrom, then type suppose 3.2, and the bond angle is 110. Then it will include some more hydrogen bond into the table. So by typing the H tab and H tab minus G, you can display all the hydrogen bond. You can label them. You can calculate the EST on these hydrogen bonds. Hope it will help, and thanks for watching the video.